Good morning, everyone. My name is Xiaoming, and I'm ESR3 from Chalmers University of Technology. Today, I will talk about the impact of system boundary on modeling results. This is the technical problem I meet in my research. Now, let me give you a simple introduction of my research. As we all know, Europe is transitioning towards a low-carbon electricity system. More and more variable renewable energy, such as wind and solar power, are being deployed for electricity production. However, there is no consensus among researchers regarding whether or not there would be large cost escalation if nuclear power is excluded for the future electricity system. For the case of Sweden, there is around 9 gigawatts of nuclear power in the system, which contributes to roughly 40% of the annual electricity production. The current Swedish nuclear fleet is getting old, and the decommission is planned for the coming decades. Therefore, there is an ongoing political discussion about whether new nuclear power plants should be invested after the decommission of the older ones. In the center of the discussion is the future electricity system costs. Therefore, in this study, we want to investigate the cost of a future low-carbon electricity system without nuclear power for Sweden. We found that previous studies in the literature focusing on Sweden either model Sweden in isolation or follow historical electricity trade pattern. One typical example is Hornet-O. In the study of Hornet-O, to replace 9 gigawatts of nuclear power, around 150 gigawatts of wind power is needed. As a result, the electricity cost is around $300 per megawatt hour, which is roughly 6 times as much as the cost of nowadays. We know from the literature that electricity trade is beneficial for the electricity system. It has 2 main functions. First, resource share. Second, variation management, especially for a large scale of wind power. Therefore, model Sweden in isolation or follow historical electricity trade pattern may underestimate the contribution of electricity trade for the future electricity system. In our study, we want to expand the system boundary from Sweden to the whole Europe and allow electricity trade between different regions. So this is the network topology for my study. Sweden and nearby countries are divided into small regions, and they are connected to the rest of Europe with transmission grids. The transmission grids can be optimally expanded. With this setup, we have a new challenge. That is how to represent the electricity system cost for a single country in an interconnected electricity system. Here is an example for 2 countries. So country A has good wind resource and a low demand. Country B has high demand, but very bad wind and solar resources. These 2 countries are connected with transmission grids. If we optimize the interconnected electricity system like this, we will see large generation capacity is invested in country A, and electricity is exported from country A to country B. If we use the conventional method to measure the system cost, which is to sum up the investment and operational costs of the system components, then country A will have a very high system cost due to large generation capacity. Country B will have a low system cost due to low generation capacity installed. But wait a minute. Do we miss something important? Yes, we miss the impact of electricity trade. Country A has large generation capacity, but can receive revenue from sending electricity to country B. Country B has low investment cost but has to pay for the imported electricity from country A. Therefore, in my study, I introduced a new indicator, which is called a nodal net average system cost. The nodal net average system cost incorporates not only the investment and operational cost of the system components, but also the revenue and the cost of electricity trade. And for this study, I will use this indicator to measure the net system cost for Sweden for different scenarios. Now let's look at the scenarios. So we have 4 base scenarios depending on the expansion of transmission grids and the availability of nuclear power. The first scenario, current transmission, no nuclear. So transmission capacity fixed to the current value. Nuclear power is not allowed for Sweden. Second scenario, current transmission, nuclear allowed. So transmission capacity fixed to the current value, and the nuclear power is generation option for Sweden. The third scenario, optimal transmission, no nuclear. And the last scenario, transmission is optimized and the nuclear power is generation option for Sweden. In the results section, I will compare the nodal net average system cost for these 4 base scenarios. Now let's look at the results. The y-axis here represents the nodal net average system cost. First, let's look at the case of current transmission. So in this case, when nuclear power is allowed for Sweden, the system cost is reduced by 3%. And in the case of optimal transmission, if nuclear power is allowed for Sweden, the system cost is reduced by 4%. So 3 and 4%. From these values, we can understand, including nuclear power for the future Swedish electricity system has a limited impact on the NATO system cost. And now let's look at the energy mix under different scenarios. So here, the y-axis represents the energy mix for Sweden, and the different colors represent the different outputs of different technologies. Blue for hydro, red for biomass, green for wind, yellow for solar, and light blue for net electricity trade. Orange color for nuclear power. Let's look at the case of fixed transmission capacity. In this case, if nuclear power is allowed for Sweden, around 25 terawatt-hour of nuclear energy is produced. And in the case of optimal transmission, if nuclear power is allowed, around 75 terawatt-hour of nuclear energy is produced. If we compare these 2 cases, we can find that the produced nuclear energy for optimal transmission is almost 3 times as much as that for the case of fixed transmission. Why nuclear is larger for this case? The answer is electricity trade. So in the case of fixed transmission capacity, Sweden is net electricity importer. And for the case of optimal transmission expansion, Sweden is a net electricity exporter. And when nuclear power is allowed for Sweden, it enables Sweden to have much larger export to the rest of Europe. By comparing the nuclear energy generation, you can see how the expansion of transmission grids would affect the system components and the trade pattern. Now let's look at the case of isolated Sweden. So in this case, Sweden is isolated. We find that surprisingly, the generated nuclear energy is even lower compared with the case there is a transmission connection. From this figure, we can see clearly how system boundary affects the invested nuclear energy in Sweden. Now let's look at a big picture for the whole Europe. Before, we have already seen that the impact of nuclear on the nodal net average system cost for Sweden in the fixed transmission case, allowing nuclear power may reduce the nodal net average system cost by 3%. And for the optimal transmission case, allowing nuclear power may reduce the nodal net average system cost for Sweden by 4%. But now let's look at the case for Europe. We can see that the columns are almost identical for each case. So for the case of fixed transmission capacity, for the case of optimal transmission capacity, allowing nuclear power in Sweden has a very minor impact on system cost for Europe. The value is almost 0. From this, we can see that even though nuclear power has a certain impact, 3 or 4% on the net system cost for Sweden. However, if we zoom the system boundary from Sweden to whole Europe, we found that allowing nuclear power in Sweden has almost 0 impact on the European electricity system cost. So all these results, the nodal net average system cost, the energy mix, and also the system cost for Europe show us the impact of system boundary on the model results. With these results, we can have a very intuitive understanding how the system boundary would affect our model results. We don't aim to provide you a common recipe how to set up a system boundary. It should vary depending on your research question, but it is always important to look at the real system boundary of your focused question and try to understand how the system boundary may potentially affect your results and carefully select the system boundary for your model. That's all. Thank you very much for your listening. If you have any questions, please send me an email. Thank you.